Hi class, welcome to lesson 59. By the end of this video, you should be able to identify and explain the processes involved in operating a battery, also known as a Voltaic cell. So you should define and identify the anode and cathode, determine the direction of electron flow, explain the purpose of a salt bridge, and explain the energy transfer in a Voltaic cell. Remember, the guided notes have been provided for you on Google Classroom, or you can take your own. Make sure you have a Regents Chemistry reference table so you can utilize reference table J as we analyze how a Voltaic cell works. Let's go. So Voltaic cells are part of a larger category of cells called electrochemical cells. In this lesson, we are going to focus on Voltaic cells. And in the next lesson, we are going to look at electrolytic. But it is a very good idea for you to write down all of the similarities and differences between these two electrochemical cells now. Voltaic cells convert chemical energy into electrical energy. That's why they're batteries. Inside a battery, there are chemicals that produce electricity. They do this spontaneously, meaning they don't need any outside energy source. In Voltaic cells, the anode has the same charge as an anion, a negative charge, and the cathode has the same charge as a cation, the positive charge. A Voltaic cell also will include a wire for electrons to flow from anode to cathode, a salt bridge that carries ions needed to maintain charge, and sometimes a voltmeter may be included, which can measure the flow of electricity. In contrast, electrolytic cells convert electrical energy to chemical energy. These are non-spontaneous reactions, meaning we have to add a power source. A very good example of an electrolytic cell is when we plug in electronics and recharge the battery. We use electricity to create chemicals that will produce electricity when unplugged. Now, the biggest difference between an electrolytic cell and a Voltaic cell is that an electrolytic cell, the anode has a positive charge and the cathode has a negative charge. Here you'll also see a wire for the electrons to flow through, but you'll also see a battery because we need a power source for this non-spontaneous reaction. So again, the similarities between the two types of cells are that they both use redox reactions. In both of the reactions, we can use a mnemonic device, anox and fat red cat. That means that the anode is the site of oxidation and the cathode is the site of reduction, and it gains mass. Electrons always flow from anode to cathode, and the anodes always decrease in size and the cathode always increases in size. That's why it's called a fat red cat, because it always increases. So here is a picture of a Voltaic cell, and we're going to walk through how this cell operates to allow chemicals to produce electricity. So on a Voltaic cell and also on an electrolytic cell, there are two solid metal pieces called electrodes, and these are the sites where oxidation and reduction occur. Now we have this mnemonic device, anox and fat red cat, to help you remember what process happens at which electrode. So the anode is always the site of oxidation and the cathode is always the site of reduction. In a spontaneous reaction, the anode, the oxidation, is always higher up on reference table J. And the less active electrode, the one that's lower on reference table J, will gain the electrons and is therefore called the cathode because it's the fat red cat. It is gaining electrons. Now, in all electrochemical cells, electrons flow across the wire, always from anode to cathode. The movement of these electrons is what essentially produces electricity. In addition, a voltaic cell, you will also have a salt bridge. The salt bridge we can see here is this connecting piece, and it has an ionic compound in it, and the salt bridge allows anions to flow towards the anode and cations to flow towards the cathode, and this is done so that we can prevent a process called depolarization, or we can maintain the charge of the anode and the cathode. So again, we can recall that the anode always loses mass as it is oxidized and it's losing electrons, and the cathode always gains mass as it is reduced. So we can again use the mnemonic device NOx and fat red cat.
Okay, so let's talk about the operation of this voltaic cell. The first two things we'll notice are there are two pieces of metal, one here, and each of those pieces of metal are called an electrode. Now, electrodes are the site of both oxidation and reduction. One electrode is the site of oxidation, and the other electrode is the site of reduction. So in order to find that, we need to look closer on reference table J. And we notice that one electrode is copper here, and the other electrode is zinc. So let's look closer on reference table J. Here on reference table J, we can see that copper is towards the bottom of the table and zinc is up here. So zinc is a better loser of electrons than copper. So that means zinc will be our anode and the electrons will flow from the zinc down to the copper. So now that we know that electrons are going to flow from the zinc, the item that is on the top of reference table J, that electrode is called the anode. And the anode is the site of oxidation or the loss of electrons. And the other electrode is called the cathode, which is the site of reduction. We can remember that with the saying fat red cat. So what we know is electrons are going to be lost by the zinc and flow through the wire in this direction towards the cathode, where they'll be gained by the copper. So if I need to write the half reactions for this entire redox process, what I know is that the zinc is being oxidized. So zinc can have an oxidation number of 2 or 0. So oxidation is an increase in charge. So this is the beginning of the half reaction for the zinc. Now it's going to go and we have to put in electrons. So these electrons are products as they're lost. They're traveling through the wire and they're going to go to the copper. And the copper is going to gain the electrons. So that means that it is going to undergo reduction. So it will have a +2 and a 0. I'm going to add those 2 electrons gained as a reactant. So notice that as we lose electrons here, we gain those electrons here. So this is the oxidation. This is our reduction. And so as this happens, what we also know is that the electron has a negative charge, so that this anode is a negatively charged electrode, and naturally the negative electrons that flow through the wire will be attracted to this positive electrode. Now this is great until we get to this point. Since this is a positive electrode, what will happen is the negative electrons will sit here and the ions in solution will combine and they will form copper atoms on the surface of the electrode. So this is why this is called the fat red cat, because the ions in the solution combine with the electrons from the wire to produce new atoms that will deposit here. But as we add negative here, that creates a problem because electrons won't want to travel if this stays negative. So the reason why the cathode is called a cathode is because cations, or positive ions, will travel through the salt bridge towards it. And the reason why the anode is called the anode is because anions from our salt bridge will travel there to maintain the charge of our electrodes. So our negative anode is going to have negative ions travel there to keep it negative. So in potassium nitrate, I have two ions. I have positive potassium and negative nitrate. So the positive potassium is going to flow towards the positive cation, and the negative nitrate is going to flow towards the negative anode. Now the other parts, again, this tube containing the ionic compound is called the salt bridge. And this instrument here, it's measuring the voltage, which measures how much electricity is flowing through this wire. This is called a voltmeter. You don't have to have the voltmeter in a voltaic cell, but it is useful if you want to know how much electrical energy is produced by this chemical reaction.
So now that we've labeled this diagram and discussed the operation, what we can use is this other mnemonic device to remember that electrons are always flowing from oxidation, where they're lost, to reduction, where they're gained. So this is effort. So let's take a minute to look through and label this voltaic cell involving both zinc and iron. Whenever we are labeling voltaic cells, make sure we are looking at reference table J.
Here we have a voltaic cell. We recall that voltaic cells always have two beakers that separate two half reactions, and they always have a salt bridge connecting those two beakers. So in order to identify where we begin the process of producing electricity, we have to use reference table J, and we have to compare the activity of the electrodes. So when I look here, I can see that zinc is more active than iron on reference table J. So the electron should flow from zinc to iron. So I can already draw in the direction of electron flow here. So electrons will flow through the wire in this direction from zinc to iron. So a couple of things to note. So we know electrons are negative, and so negative electrons should be drawn to the positively charged electrode, and they should come out of the negatively charged electrode. And notice that this electrode is where the electrons are lost. So that we remember that the loss of electrons is oxidation, and we have that other mnemonic device, anox. So this electrode is called the anode. The negative electrode of a voltaic cell is the anode, and electrons will leave the anode and travel towards the positively charged electrode where electrons are gained. The gain of electrons is called reduction, and we have this other saying, fat red cat. So what we know is that this is called the cathode, and it is gaining electrons, that's why it's fat, as reduction is occurring at the cathode. And so if we wanted to write the half reactions of what's going on here on this half reaction, we have zinc with a +2 charge, and the electrode has a 0 charge. And so we're going to write an oxidation half reaction. Oxidation means that the charge should increase. So we're going to end with a +2 and we're going to start with a 0. So this is an increase in charge, and we'll put our electrons that are lost in, and we put them on the more positive side. So we have 2 electrons for each zinc atom flowing through the wire, and they are deposited here on this positively charged cathode where reduction is occurring. So for this half reaction, we have iron 3, and this iron electrode has a 0 charge. So my oxidation half reaction was here, and so to write the reduction half reaction, we're going to show that iron 3 decreases in charge, and we're going to add the electrons that are gained on the more positive side. So here my electrons are gained. So electrons are flowing through the wire from the zinc, and they're going to the iron. Now, what happens with the electrons is the iron atom does not want to gain the electrons. It actually wants to lose electrons, but those electrons will be attracted to the iron ions in solution. So the iron ions will take the electrons and form iron atoms. That causes iron atoms to form on the surface of this electrode. So this electrode is a fat red cap because atoms are forming. We can see them here on the product side on the surface of this electrode. Now, the last thing that we need in order to maintain the circuit is we have to make sure that our cathode stays positive, even though it's gaining electrons, and our anode stays negative. In order to do that, in comes the salt bridge. So in the salt bridge, we're going to have positive cations and negative anions. And the cations will always flow towards the cathode. And the anions will always flow towards the anode. And this shows a complete circuit or circular shape of moving charge.
Here's another voltaic cell with lead and zinc. Remember that when labeling and describing the operation of voltaic cell, you'll always want to make sure you have out reference table J.
You can tell that it's voltaic because we have two separate beakers that are connected by a salt bridge. Here you'll notice something a little bit different in our circuit. Our switch is open. It's literally just like a light switch. So when the switch is open, electrons cannot flow in a circuit because the wire is disconnected. But when we close the switch, we'll be able to connect the circuit and we'll allow the free flow of electrons. So electricity can flow. This works the same way a switch works, like a light switch. When the light switch is off, we open up the wire, we disconnect it so electricity or electrons are not flowing. And when we close it, we allow the flow of electrons. So the first thing we notice is we have a lead electrode and a zinc electrode. So we'll go to reference table J and compare their activities. In this case, zinc is more active than lead, so electrons should flow from zinc to lead. So in this case, the electrons are going to flow in this direction from the more active zinc to the less active lead. And so notice that zinc is losing electrons and it's undergoing oxidation. So that means that the zinc is also called our anode. And our anode, which gives off negative electrons, has a negative charge, similar to an anion. And on the other side then, we have the gain of electrons, which is called reduction. This is the fat red cat. And so our lead electrode is called the cathode, and it has a positive charge. So electrons are flowing in this direction, and then we need the charge to continue to flow in a circular manner. So what we're going to have is in the salt bridge, again, anions, which are negative, always flow towards the negative anode. And cations will flow towards the positive cathode. And so now we have a complete circuit of negative flowing charge going through our circuit. And if you want, we can write the half reactions for each. And so we can also use down here to break up to help us write the half reaction. So we can see that the zinc is changing from the atom to a higher charged ion, and it is losing 2 electrons, which flow through the wire toward the lead, and our lead ions that are in the solution are going to gain those 2 electrons and form lead atoms on the surface of the electrode, thus making it fatter or heavier as it gains mass.
Can you label the anode and cathode, direction of electron flow, and the direction of ion movement in the salt bridge for this voltaic cell? Try it out yourself, and then we'll talk about it. In summary, we know that voltaic cells are spontaneous chemical reactions where chemical energy is converted to electrical energy. Many times we call voltaic cells batteries, so they look very different from the batteries you use inside of your electronic devices. So the batteries we'll look at are very rudimentary. But always electrons flow from anode to cathode. The anode has a negative charge and is higher up on reference table J. This concludes lesson number 59, Voltaic Cells. Make sure you've taken great notes and completed your homework, and I'll see you in class.
So here, again, we use reference table J, and we can see from reference table J that magnesium is more active than copper. So electrons will flow from magnesium to copper. So we're losing electrons here, which is oxidation. So this is our anode. And the negative electrons come out of the anode, and they are attracted to the positive cathode. So here we're gaining electrons, which is called reduction. And we know this is also called the fat red cat. And that means that this is called the cathode, which has a positive charge. And we're undergoing reduction. So the half reaction here, the oxidation half reaction, is when magnesium atoms turn into magnesium ions, and they lose 2 electrons through the wire. Then those 2 electrons are accepted by the copper ion to produce copper atoms. So here we can see the charge is going down and we're gaining electrons. The last thing we want to know is how are the ions moving through the salt bridge, but the anions move to the anode always. So the negative ions are traveling here. So when we look at the negative charges, notice how they're flowing in a circuit. And then just to counterbalance this, the positive cations are moving towards the cathode.